In this video, we are going to talk about some of the properties, characteristics of ellipses before we get into the equations and the math of it. I'm pulling the images from a website called coolmath.com. It's kind of old, but it has a pretty good representation of some of the properties in it. Remember that it's part of a conics, and conics are taking slices of a cone. So if we take a slice of a cone on an angle, we're going to naturally create an ellipse. So we're going to be talking about the equations of it. But there is some kind of interesting properties that exist. So one of them is you have these points, and they're going to be known as focal points. And these 2 points that if you were to find the distance between the focal points to any point on this edge, that if you add them together, it's always the same. Which, not coincidentally, that is actually how you draw a perfect ellipse. Is you take a string, you basically nail 2 spots, or it's suggesting to put 2 nails onto a board, and take a string that's a little bit longer than whatever that distance is between them, and pull it taut, and as you pull it taut, you will just naturally make an ellipse. All right, so I thought that was kind of neat to see. But one thing that I think is really interesting is those focal points. There's definitely something else going on with that. Every orbit of all the planets are not circles, they're all ellipses. Some are more circular than others, and some are more elliptical than others. But comets, like Halley's Comet, will have very, very elliptical kind of a path around. But here's one of the interesting things. The reflective properties. Like a parabola, there are some reflective properties on an ellipse. So if you send something in a direction, so if you made a putt-putt golf thing, and if you were to hit and you made the hole a perfect ellipse, and you started here and you ended here, assuming there's no spin or anything that affected it, if you were to hit it in any direction, it would perfectly go right to the hole. So, something interesting about that is light would travel like that, but more importantly, sound would travel like that. So, there is a legend that in one of the rooms in the Capitol building in Washington, D.C., one of the founding fathers knew the property, or whenever it was built, that they put their desk on one of the focal points, and then they knew where the other focal point was in the room, and they would have people talk. And so they would sit and say, you know what, why don't you guys talk about it? And they had them face away. So the people were facing this wall. But little did they know that the person would stand on the other side at the focal point, and the 2 people would talk, and their voice would basically spread out, but then their voice would refocus back onto the one point that the other politician was standing in. So legend has it that that's true. Well, there are museums that have that. This is a hallway between 2 exhibits in Chicago, the Museum of Science and Industry, and it's called a Whispering Gallery. That if you stand on one focal point, you stand on the other focal point. The idea is that you talk in such a light voice that the person can't hear you. Then you turn around and talk into this kind of dome thing, and the ceiling is a 3-dimensional ellipse. And so as you speak, your voice spreads, but then it refocuses and reflects right back to that person, and they can hear you as if you're standing right next to them. So, legend might be true. So, but I thought that was kind of an interesting thing, that everything kind of reflects and refocuses back on it. So those focal points are going to play a role when we start to graph it, but that was just kind of a little more real-life application to it. So we'll start doing the math and doing the equations, and let's get we'll get some graphs drawn.